Imagine you're standing in the middle of a large open field on a very clear night. You look up and you see stars, thousands of them. It's a beautiful sight, isn't it? Now, if you're like me, you start wondering. You look at one star and think, how far away is that? Then you look at the space between the stars and think, what's back there? You keep going further and further until you hit a wall in your mind. You ask yourself, is there an edge? And if there is, what's on the other side of it? It's a funny thing about humans. We always want to know what's over the next hill. When we were primitive, it was the next forest. Later, it was the ocean. Now it's the whole sky. But the universe is a big word. It's supposed to mean everything. So asking what's beyond everything sounds like a trick question, doesn't it? It's like asking what's north of the North Pole. But nature is much more clever than our language, and she has some very interesting secrets hidden in the math. To understand the beyond, we first have to understand our own here. We live in a sort of bubble, not a physical bubble with a glass shell, but a bubble of time and light. We call this the observable universe. Think of it like this. If light travels at a certain speed, and it does about 86,000 miles every single second, and the universe has only been around for a certain amount of time, then there is a limit to how far we can see. If a star is 20 billion light years away, and the universe is only 13 or 14 billion years old, that star's light simply hasn't had the time to reach our eyes yet. It's out there, but for us it might as well not exist. So our first edge isn't a wall, it's a horizon. It's exactly like standing on a ship in the middle of the ocean. You see a circle of water around you, you know more water exists beyond that circle. But from where you're standing, you can't see the whales or the islands that are 50 miles away. The horizon moves with you. If you flew in a rocket toward the edge of our observable universe, the horizon would just keep pushing back, revealing more stuff that was previously hidden in the dark. But then people ask, okay, but is the stuff infinite? Does the ocean of stars just go on forever and ever without end? Or does the whole thing eventually stop? This is where the math gets really fun. Most people think of space as a big, empty room, an empty box. You put things in the box, galaxies, planets, atoms. But Einstein showed us that space isn't a box. Space is more like a piece of material. It can stretch, it can ripple, and most importantly, it can curve. Think about a bug crawling on a giant ball. The bug thinks the world is flat. It crawls forward in what it thinks is a straight line. It never hits a wall, it never sees an edge, but eventually, to its great surprise, it ends up right back where it started. The ball is finite. It has a specific size, but it has no boundary. It has no beyond in terms of its own surface. Now imagine our whole universe is like that, but in 3 dimensions instead of 2. We could travel in a straight line past billions of galaxies, and if we went long enough, we'd see the back of our own heads. If that's the case, asking what's beyond the universe is like the bug asking what's under the surface of the ball. The bug's whole world is the surface. For us, our whole world is space and time. To go beyond might mean stepping out of space and time altogether. But let's get back to the stuff inside. When we talk about the beginning of this whole mess, the Big Bang, people often picture a tiny firecracker exploding in a big dark room. They think the firecracker is the universe, and the dark room is the beyond. But that's not it at all. According to our best equations, the Big Bang was the expansion of space itself. There was no outside. Imagine you have a piece of stretchy rubber. You draw dots on it to represent galaxies. Now, you stretch the rubber, the dots move away from each other. They aren't moving through the rubber between them is getting bigger. Now, if you shrink that rubber back in your mind, the dots get closer and closer. Eventually, they are all on top of each other. The rubber itself becomes a single point. When you get to that point, our current math starts to act very strange. We call it a singularity. In calculus, we talk about limits. You can get closer and closer to a value without ever touching it. If you have a fraction like 1x, and you make x smaller and smaller, the number gets bigger and bigger. When x becomes 0, the math blows up. It goes to infinity. Nature usually doesn't like infinities. Whenever we see an infinity in our notebooks, it's a giant sign from the universe saying, hey, you don't know what you're talking about here. Try harder. This brings us to a very deep realization. Our understanding of beyond is limited by our understanding of small. To understand the giant scale of the universe, you have to understand the tiny scale of atoms. Everything is connected. If you look at the very beginning, the whole universe was smaller than an atom. And at that scale, things don't act like billiard balls. They act like waves. They act like ghosts. In quantum mechanics, there's a thing called the uncertainty principle. It says you can't know everything about a particle at once. The more you know about where it is, the less you know about where it's going. This means that at the very root of reality, everything is a little bit fuzzy. Even empty space isn't really empty. If you look closely enough at nothing, you'll see it's actually a boiling soup of energy. Particles are popping into existence and disappearing before you can say hello. So if space itself is made of this quantum foam, then the beyond might not be a place in space. It might be a different state of being. We might be living on the surface of something much deeper and much more complex. People often get intimidated by the math, but calculus is just a way of describing how things change. It's a language for talking about if you want to know how fast a car is going at one specific moment, you look at how far it went in a very small amount of time. Then you make that time even smaller and smaller, until it's infinitesimally small. When we apply that kind of thinking to the universe, we realize that the edge might be a matter of perspective. We look out and see light from billions of years ago. We are looking back in time. The further we look, the closer we get to the beginning. The beyond isn't just a place far away in kilometers. It's a place far away in seconds. I remember once looking at a drop of water and thinking about all the life in it. To a tiny microbe, that drop is the universe. It has its own physics, its own boundaries of surface tension. It doesn't know about the sun, or the trees, or the person looking through the microscope. We are a lot like that microbe. We are looking at the surface tension of our universe, the speed of light, the curvature of gravity, and we are trying to guess what the rest of the laboratory looks like. One of the most exciting ideas in modern physics is that our Big Bang wasn't a unique event. If you have a vast ocean of this quantum energy, maybe bubbles are popping up all the time. Each bubble would be its own universe, with its own stars and maybe even its own laws of physics. In one bubble, gravity might be so strong that everything collapses in a second. In another, it might be so weak that atoms never form. We just happen to live in a bubble where the rules allow for people who like to sit around and wonder about bubbles. This idea doesn't require advanced magic. It just requires taking the math we already have and following it to its logical conclusion. It's like discovering that your house is part of a city. You might never leave your front door, but the fact that the city is there changes how you think about your house. Now think about the light cone. It's a way of mapping what we can influence and what can influence us. Anything outside that cone is elsewhere. It's physically impossible for us to touch it or see it because light can't get there fast enough. That elsewhere is a type of beyond that exists right now, all around us. There are galaxies having nows at the same time. We are having ours, but we will never, ever know about them. They are beyond our reach. Is that frustrating? Maybe, but I find it wonderful. It means the world is much bigger than our ability to see it. It means there's always going to be a mystery. Some people want a final answer, a God equation that fits on a t-shirt and explains everything. But nature has a way of being much more layered than that. Every time we peel back a layer from atoms to nuclei, from nuclei to quarks, we find a whole new world of complexity. So when we ask what is beyond the universe, we are really asking, what is the next layer? Is it more space? Is it other bubbles? Is it a mathematical structure we can't even visualize yet? To even begin to answer that, we have to be comfortable with the idea that our common sense is usually wrong. Common sense is something we develop to avoid being eaten by tigers on the African savanna. It's very good for judging how fast a rock falls or how to jump over a stream. It is not very good at judging what happens at the speed of light or what happens when you compress all the matter in the world into the size of a marble. For that we need the math. The math is like a pair of glasses that lets us see things our eyes can't. It tells us that space can stretch, that time can slow down, and that nothing is actually something. When you start to play with these ideas, the universe stops being a cold, empty place and starts being a dynamic living thing. It's a happening. It's a process, and we are a part of that process that has developed the ability to look back at itself and go, in the next part of this discussion, we're going to look at some of the wilder theories, the things that sound like science fiction, but are actually being debated by serious people with chalk on their hand. We'll talk about how there could be other versions of you out there, and how the universe might be a giant hologram. But for now, just sit with the idea that the edge isn't a wall. It's an invitation. We are living in a tiny corner of a magnificent, unfolding story, and we've only just finished the first page. Think about the sheer scale of it. If you took a grain of sand and held it at arm's length against the sky, that tiny speck covers thousands of galaxies. Each of those galaxies has billions of stars, and that's just the part we can see. The part we can't see is likely much, much larger. It's like we're living in a tiny lit room in a vast mansion at night. We can see the furniture near the lamp, but we can only guess how many other rooms there are, or how high the ceilings go. But the beautiful thing is the laws of physics we learn in this room, the way light bends, the way energy is conserved, seem to apply in the other rooms too. We can use the light from our little lamp to peer through the doorway and make some very good guesses about the rest of the house. That's the power of science. It's the tool we use to turn the beyond into the known. So don't be afraid of the vastness. Don't be afraid of the beyond. It's just more of the same beautiful, crazy, wonderful nature that we see right here under our noses. It's all one piece. We just have to keep looking, keep asking, and keep being surprised by how simple and yet how incredibly complex the whole thing really is. Think about a simple radio. You turn the dial and you hear music. Then you turn it again and you hear a news report. Then you turn it again, and it's a sports game. All those signals are in the room with you right now. They are passing through your body, but you only hear the one you're tuned to. Our universe might be a lot like that. We are tuned to a certain frequency of space and time, but that doesn't mean the other stations aren't playing. The beyond might be right here, vibrating in a way we haven't learned to listen to yet. We used to think heat was a fluid. We were wrong. It's just atoms jigging around. We used to think the air was empty. We were wrong. It's a thick soup of molecules. Every time we thought we hit a limit, it turned out to be a doorway. And that's the most important thing I want you to take away from this. There are no no-go zones in the search for knowledge. If there's something out there, we can eventually figure out a way to study it. Maybe not today, maybe not in 100 years, but as long as we keep the spirit of curiosity alive, the beyond will always be getting a little bit closer. So let's keep our eyes open. Let's keep playing with the equations and looking through the telescopes. Because the universe is much more than just a place where we live. It's a giant puzzle, and we are the pieces that are trying to put it together. And I don't know about you, but I think that's a pretty good reason to get out of bed in the morning. So we've talked about our little bubble, our observable universe, and how it's really just a matter of how far light has managed to travel since the whole thing kicked off. But now comes the real fun. Now we get to stick our heads out of the window and see what else might be out there. And I have to tell you, the ideas get pretty wild. But they aren't just wild guesses. They come from looking at our equations and saying, wait a minute, if this part is true, then that part has to be true too. It's like finding a single bone and realizing it must belong to a giant dinosaur you've never seen. One of the biggest clues we have comes from a problem with the smoothness of the universe. When we look at the sky in every direction, the temperature of the deep space is almost exactly the same. It's like a cup of coffee that's been sitting on a table. Eventually it becomes the same temperature as the room. But the universe is so big that there hasn't been enough time for the hot parts to talk to the cold parts and even things out. So why is it so uniform? The answer we've come up with is something called inflation. It's the idea that for a tiny, tiny fraction of a second, we're talking about a decimal point, followed by 30-odd zeros, and then a 1. The universe didn't just expand, it exploded in size. It grew faster than the speed of light. Now you might say, hold on, I thought nothing goes faster than light. And you're right, inside space, nothing does. But space itself can do whatever it wants. It can stretch as fast as it likes. This inflation did something amazing. It took a tiny microscopic patch of space and stretched it out so much that it became our whole visible universe. But here's the kicker. Why would inflation stop? Our math suggests that in most of the meta-universe, inflation is still going on right now. It's like a giant ever-growing sea of energy.
Every once in a while, a little patch of that sea slows down and stops inflating. When it stops, all that energy turns into matter and heat. It creates a big bang. Our universe is just one of those little patches. It's a bubble in a cosmic ocean that is constantly producing new bubbles. This is what we call the level 2 multiverse. It's not just a beyond more stars. It's a beyond of entirely different universe. Now you might ask, are those other bubbles like ours? Well, that's where things get really spooky. The laws of physics we see, the strength of gravity, the charge of an electron, might just be local rules. Imagine you have a big piece of metal. In one spot the atoms are lined up one way, making it magnetic. In another spot they might be lined up differently. In the same way, each bubble universe might have different settings for the fundamental constants of nature. In some bubbles, gravity might be so strong that the whole thing crunches back down into a point before a single star can form. In others, space might expand so fast that atoms can't even hold together. We live in a bubble that has the just right settings for life. It's not that the universe was designed for us. It's just that we can only exist in the version of the universe where the rules allow us to exist. It's like a fish thinking the ocean was designed for it because it has water. If there were no water, there'd be no fish to do the thinking. This leads us to a very deep concept in calculus and probability. If you have an infinite number of these bubbles, and each one has a different set of rules, then every possible version of a universe must exist somewhere. Somewhere out there, there's a universe where gravity is slightly weaker. Somewhere else, there's a universe with 4 dimensions of space instead of 3. And if you have enough of these bubbles, eventually you'll get one that looks exactly like ours, identical, with another planet Earth, another room, just like this one, and someone who looks exactly like you, wondering about the same thing. It sounds like science fiction, doesn't it? But it's just a statistical necessity, if the beyond is truly infinite. But let's talk about another kind of beyond. This one isn't far away in space. It's parallel to us. This comes from quantum mechanics, the study of the very small. I spent a lot of my life playing with these equations, and they are the most successful rules we've ever found. But they are also the most confusing. In the quantum world, a particle doesn't just have one path. It takes every possible path at the same time. When we look at the particle, we see it in one place. But where did the other paths go? One interpretation, the many worlds theory, says that the universe actually split. Every time a quantum event happens, the universe branches into different versions. In one branch, the particle went left. In another it went right. If this is true, the beyond isn't just out there. It's right here, layered on top of us, in a giant branching tree of possibility. There's a version of reality where you chose a different breakfast this morning, and a version where the dinosaurs never got hit by that asteroid. These branches are physically real, but they are decoherent. They can't talk to each other anymore. They've gone their separate way. It's like a set of radio waves, all occupying the same room, but tuned to different frequencies. You can't hear the other stations, but that doesn't mean the music isn't playing. Now I know what you're thinking. Richard, this is getting a bit much. How can we ever know any of this? That's the right question to ask. In science, if you can't test it, it's just a story. And right now, we can't hop in a boat and visit another bubble universe. But we can look for fingerprints. If another bubble universe bumped into ours early on, it might have left a bruise in the cosmic microwave background, the leftover heat from the Big Bang. People are looking for those bruises right now with satellites. We're also looking at the math of string theory, which tries to unify gravity with quantum mechanics. String theory says that what we think are particles are actually tiny, vibrating strings, and for those strings to vibrate the way they do, they need more than 3 dimensions. They need 9 or 10. Where are those extra dimensions? We think they're curled up so small that we can't see them. Imagine a garden hose. From a distance, it looks like a 1D line. But if you're an ant crawling on it, you realize there's a second dimension. You can crawl around the hose. We think our universe might have these extra dimensions beyond our reach, because they are so tiny, but they affect how the world works. They determine the masses of particles and the forces of nature. So the beyond might be tucked inside every single atom in your body. There's another idea that's even crazier. And I love it because it's so elegant. It's called the holographic principle. It started with thinking about black holes. When you throw something into a black hole, the information about that object, what it was made of, its color, its shape, seems to get stuck on the surface. The event horizon, it's like the 3D object, is flattened into a 2D description on the shell of the hole. Some physicists have realized that the same logic might apply to the whole universe. Maybe everything we see, all the 3D space, the galaxies, the people is just a projection of information that lives on a 2D surface at the very edge of the universe. Think about a credit card hologram. It's a flat, 2D plastic surface, but when you tilt it, you see a 3D image with depth. If the holographic principle is right, then we are the 3D image, and the real stuff is the information on the boundary. In this view, the beyond is the source code. It's the fundamental information that builds the world we experience. It changes the whole way we think about space. Space might not be a real thing at all. It might be an emergent property, like the temperature of a gas. A single molecule doesn't have a temperature, but a billion of them jigging around does. Maybe space is just what it looks like when a billion pieces of information interact. This is where the calculus of information comes in. We're starting to treat the universe not as a collection of stuff, but as a collection of bits. And just like you can describe a complex curve with a simple equation, we're trying to find the simple equation for the universe's information. It's a huge challenge. It's like trying to figure out how a computer works just by looking at the pictures on the screen. But we're getting there. We're learning how to read the pixels. I've spent my life looking at the world and trying to figure out the rules of the game. And the most important rule I've found is that nature is always more imaginative than we are. We think we've found the final answer, and then nature says, wait, look at this, and opens a whole new door. The idea of a multiverse, or extra dimensions, or holograms, might turn out to be wrong, but even if they are, the truth is likely to be even stranger. I remember as a kid, I had a book about insects. I was fascinated by how a bee sees the world. It sees ultraviolet light that we can't see. To a bee, a plain white flower has a landing strip of patterns leading to the nectar. The bees beyond is a part of the world that is invisible to us. Science is just our way of building ultraviolet eye. We build telescopes to see the past, and we build particle accelerators to see the small, and we use math to see the beyond. When you look at the cosmic microwave background, that static you used to see on old TVs between channels, you're looking at the very first light that ever traveled through the universe. You're looking at the shell of our bubble, and when we analyze the tiny ripples in that light, we are seeing the echoes of the quantum foam from the very beginning. We are seeing the fingerprints of the beyond. It's a direct connection between the biggest thing we can imagine and the smallest thing we can calculate. So what exists beyond the universe? Maybe more space, maybe other universes with laws of physics that would make your head spin, maybe a 2D surface of information, or maybe something so different that our languages don't even have words for it yet. But whatever it isn't supernatural. It's just more nature. It's just more of this wonderful, logical, mysterious puzzle we find ourselves in. People ask me if I feel small when I think about how big the universe is. And I say no, I feel big, because even though I'm just a tiny speck of carbon on a little blue rock, I'm a speck of carbon that can understand the whole thing. My brain, which is only a few pounds of meat, can contain the idea of a billion light-year wide galaxy. It can calculate the path of a photon. It can wonder about what's beyond the edge of time. That's a miracle, not a magic miracle, but a natural one. We are the part of the universe that has started to look at itself and ask questions. And don't worry if you don't understand every bit of the math. I've been doing this for decades, and there are days when it doesn't make sense to me either. The math is just a tool. The important thing is the feeling of the thing, the realization that the world is much deeper than it looks on the surface. When you walk away from here today, I want you to look at a tree, or a cloud, or a star, and think, that thing is part of a story that goes back 14 billion years, and might go on for trillions more, and it might be just one tiny part of a much bigger ocean. Nature is like a giant onion. You peel back one layer of mystery, And there's another one underneath, and another one. Does it ever end? Is there a core? That is the absolute truth. I don't know, but I do know that the peeling is the best part. The discovery is the joy. Whether there are a million universes, or just one, the fact that we can even ask the question is what makes being alive so incredible. The beyond isn't a place to be afraid of. It's the frontier. It's the place where the next great adventure is waiting. We've mapped the coastlines of our little island, and now we're starting to build ships to see what's across the sea. Some people say we should stay on the shore where it's safe, but that's not who we are. We are the explorers. We are the question askers. And as long as there is a beyond, we will be trying to get there, one equation at a time. I want to leave you with one last thought. Science isn't about having all the answers. It's about being okay with not knowing. It's much more interesting to live with doubt and uncertainty than to have answers that might be wrong. If you're not sure about something, you keep looking, you keep checking, you keep paying, and that's how we find the truth. The beyond is the ultimate uncertainty, and that's why it's the most exciting thing in the world. So keep looking up, keep wondering why, and never ever stop being surprised by the world, because it's a lot bigger, a lot stranger, and a lot more beautiful than you can possibly imagine. We're all in this together, on this little rock, floating in a vast, mysterious everything. And isn't it wonderful that we get to be here and see even a little bit of it? It's been a real pleasure talking with you. Physics is a lot of hard work, but it's also the best game in town. I hope you go out and find a little bit of that beyond in your own life, whether it's in a book, through a telescope, or just by looking at a drop of water and realizing there's a whole world inside it. There's always more to learn. There's always more to see. And I, for one, can't wait to see what we find next.